In this section, we will learn about the cross product, which is another operation between vectors. It's an interpretation of vector multiplication, the second one that we've seen so far. The first was the dot product. We could take the dot product of any two vectors of the same dimension. That result would be a scalar. The cross product is going to be a little bit different. So the cross product is this second multiplication interpretation. Cross product only works in 3 dimensions. We will only think of 3-dimensional vectors when we find the cross product. It is not defined for other dimensions. The definition here is going to be using 3-dimensional vectors. If we had a couple 2-dimensional vectors, say a1, a2, and try to find the cross product of that with another 2-dimensional vector, b1, b2, this is not defined. Cross product only works in 3 dimensions. Let's write down the definition of a cross product. It might seem a little bit arbitrary, but we'll see some useful geometric applications of this definition, which is why we choose to define the cross product this way. The cross product of two 3-dimensional vectors is another 3-dimensional vector. The first component of this new vector is a2 times b3 minus b2 times a3. That's the first component. The second component is b1 times a3 minus a1 times b3. The third component is a1 times b2 minus b1 times a2. The cross product of two 3D vectors is another 3D vector, and this is how we choose to define it. This definition is kind of complex looking, wouldn't you agree? So let me give you some tidbits for trying to understand and memorize this. First of all, notice that each component has the same general form. We're subtracting two things by each other. Notice also that the first component of the cross product does not have any a1s or b1s. The second component does not have any a2s or b2s. The third component doesn't have any a3s or b3s. So each component of the cross product is missing the corresponding components from the original two vectors. Let me point out a pattern here. The first component, let's just think of a-b-b-a, ABA, and the second component b-a-a-b, Bob, and then the third component a-b-b-a. So if you can think of ABA, Bob, ABA, that might help to memorize this form. Think of ABA, Bob, ABA, and keep the orders of the numbers in increasing order. Notice how we have a 2, b3. The numbers always go up. 1, 3, 1, 3, 1, 2, 1, 2. I don't know if that helps you memorize this expression at all. It helps me to keep track of it, but whichever way works best for you to memorize this formula, you want to learn the definition of the cross product. If you've learned linear algebra before, let me show you another way of writing down this formula. We can think of the cross product as a determinant of a 3x3 matrix. We can take the 3x3 matrix where the first row is I, J, K. The second row is the vector A, A1, A2, A3. And the third row is the vector B, B1, B2, B3. If we take the determinant of this 3x3 matrix, we will get exactly the cross product vector that we just defined in IJK notation. So if you're comfortable with computing determinants of 3x3 matrices, you can memorize the formula this way. If you don't know what a 3x3 matrix or a determinant is, don't worry about this at all. Just memorize the formula in this form. Now that we've seen the basic formula, let's see how we can view the cross product geometrically. The cross product, A cross B, will always be a vector. Remember that the dot product results in a scalar. Cross product results in a vector. It's always a 3-dimensional vector. And it turns out that this vector is always perpendicular to both of the starting vectors, to both A and B. How could we verify this? How could we verify that the cross product is perpendicular to both A and B? Well, we could find A dot the cross product, and we'd see that we'd get 0. Let's quickly do that. We want to check that the vector A is perpendicular or orthogonal to the vector A cross B. How do we determine if two vectors are orthogonal? We take the dot product. I want to compute A dot A cross B. I'll go ahead and write these out in general. A is the vector A1, A2, A3. And A cross B is exactly what we just wrote down. So we are dotting A with A2, B3 minus B2, A3, comma, B1, A3 minus A1, B3, comma, A1, B2 minus B1, A2. Multiply the corresponding components together now. We're doing a dot product because we want to check that A is actually perpendicular to A cross B. So A times the first component, we have A1 times A2B3 minus B2A3, plus A2, second components multiplied together, times B1A3 minus A1B3. Finally, we take the third component, multiply that by the third component of the cross product, and we add together A3 times A1B2 minus B1A2. We have some alphabet soup going on here, but this will all simplify to 0. Let's expand this out. From this first term, I have A1 times A2 times B3 minus A1, B2, A3. Let's write that out. I'm just distributing here A1, A2, B3 minus A1, B2, A3 plus, now expand out, distribute in this second term, A2, B1, A3 minus A2, A1, B3. Finally, in the last term, we have A3, A1, B2 minus A3, B1, A2. Now watch how things cancel. A1, A2, B3, that's A1, A2, B3, just written in a slightly different order. A1, B2, A3, I can cancel by A1, B2, A3 right here. Again, just slightly a different order in the product. A2, B1, A3, A2, B1, A3, those cancel out. We are left with 0. The dot product of A with A cross B is 0. That means that A is perpendicular to the cross product. And we just verify this in general. This is a proof that works for any three-dimensional vectors. We could do the same thing with the vector B. If we find B dot A cross B, we would also get 0. All of this messy arithmetic just tells us that the cross product will always be perpendicular to vector A, and it turns out that it's always perpendicular to vector B as well. Let's draw some vectors to try to visualize this. We'll draw a vector A here, and then a vector B. These are supposed to be in 3 dimensions, so just try to visualize this configuration somehow floating around in 3 dimensions. The cross product, A cross B, is a third vector that's perpendicular to both A and B. The direction of this perpendicular vector is given by the right-hand rule. We saw this before for labeling the coordinate axes of the XYZ coordinate system, and the same kind of principle works with the cross product. To find the direction of the cross product vector, which is perpendicular to both A and B, point your forefingers in the direction of the starting vector, and then curl them towards the other vector in the smaller angle. So I don't curl around this way because that's more than 180. I point my fingers in the direction of A and curl them toward B in the smaller angle. My thumb will then automatically point in the direction of the cross product vector. So the cross product is going to be perpendicular, sort of coming out of the page, and it creates a right angle with both A and B. This would be A cross B. On the other hand, think of finding B cross A, just switch the order. If we find B cross A, we would point our forefingers in the direction of B and then curl through the smallest angle. So take your right hand, point the forefingers of your right hand in the direction of B, your thumb should be facing the screen, and then curl your forefingers toward the vector A. Your thumb will point in the direction of the cross product, straight into the screen. So the cross product B cross A goes in the completely opposite direction. This would be B cross A. Once again, it's perpendicular to both A and B, and this is really hard to visualize in 2 dimensions like this. So in a little while, we'll verify this in GeoGebra. Let's talk about some more geometric properties of the cross product. If we think of the angle theta between the 2 vectors, there is a geometric interpretation for the magnitude of the cross product vectors. Let's draw some new vectors to visualize this. We've got a vector A and a vector B. The angle between them is right here. This is theta. Turns out that the magnitude of the cross product is equal to the magnitude of the vector A times the magnitude of the vector B times the sine of the angle between them. We saw a very similar formula for dot product. The dot product of 2 vectors is magnitude of A times magnitude of B times cosine of the angle between them. We have a very similar looking expression for the cross product. However, cross product is a vector. When we find magnitude of A times magnitude of B times sine of the angle, this here is a scalar. So this scalar is equal to the magnitude of the cross product vector. There's one more geometric property of cross products here. Geometrically, this magnitude means something in terms of the picture. If we write a parallelogram determined by the 2 vectors, the area of that parallelogram is equal to the magnitude of the cross product. Here's what the parallelogram looks like. We would write B over here, and then we'd write A over here. This is a parallelogram, and the area inside this parallelogram is equal to the magnitude of the cross product vector. We really have some rich geometric properties of the cross product. Let's summarize these in a simple statement. A cross B is a vector that is perpendicular to both A and B. The way to figure out which direction it goes perpendicular to A and B is to figure out the orientation given by the right-hand rule. The magnitude of the cross product vector is equal to the magnitudes of the two vectors times the sine of the angle between them. And that also corresponds to the area formed by the parallelogram described by the vectors. Now let's practice solving some problems involving the cross product. In example 1, we simply want to find the cross product of A and B. So our vector A is 2, 1, 1. B is the vector -1, 4, 3. And we want the cross product, A cross B. The first component in the cross product is formed by taking the second and third components from the original vectors. 1 times 3 minus 4 times 1. Perhaps this is why it's called cross product, because we can think of sort of crisscrossing in the vectors here. So A2 times B3 minus B2 times A3, that's the first component. A2 times B3 minus B2 times A3. For the second component in the cross product, we ignore the second component in our original vectors, and we take -1 times 1 minus 2 times 3. -1 times 1 minus 2 times 3. And the final component, we just take the first two components from the starting vectors, 2 times 4 minus -1 times 1. I'll just mention here that when you're first learning the cross product, it's really easy to make algebraic mistakes here. So just keep practicing with it, and pretty soon you'll get into the rhythm of finding the cross product pretty easily. Now let's simplify to get the final vector. 1 times 3 is 3, minus 4 times 1. -1 times 1 is -1 minus 6. And then the final component is 2 times 4, 8, minus a -1, 8 plus 1. So 3 minus 4, that's -1. -1 minus 6, -7. 8 plus 1 is 9. That is the cross product of these two vectors. So our answer for part A is -1, -7, 9. Let's take a look at example 2. We want to verify that this cross product is perpendicular to both A and B. How do we verify that? We need to find the dot product of this with the original two starting vectors. So this is our cross product, A cross B. And this cross product should be perpendicular to both A and B. Let's double check that in example 2. We're going to start with A dot A cross B, and we prove this in general, but we'll do it here with a numerical example. So A is the vector 2, 1, 1, and we are dotting that now with the cross product, which we just found, -1, -7, 9. Dot product is much easier to compute than the cross product. 2 times -1, -2, 1 times -7 minus 7, 1 times 9 plus 9. -2 minus 7 plus 9, yes, that simplifies to 0. Since the dot product is 0, that means A is perpendicular, or orthogonal, to A cross B. Do the same with the vector B real quick. B dotted with A cross B. Well, B is the vector -1, 4, 3. And we're dotting that with the cross product, -1, -7, 9. -1 times -1, positive 1, plus 4 times -7, that would be -28. So 1 minus 28. And 3 times 9 is 27, so we add 27. 1 minus 28 plus 27, yes, that also simplifies to 0. So we've verified, we've checked, that both A and B are perpendicular to the cross product. Let's visualize this in 3 dimensions using GeoGebra. Here in GeoGebra, we're going to start with the vector A, which is 2, 1, 1. There it is. Let's just remember how vectors are sketched in 3 dimensions. 2, 1, 1, that means we go 2 in the x direction, that's the red axis. We go 1 in the y direction, that's the green axis. And then we go up 1 in the z direction, that's the blue axis. And that's our vector 2, 1, 1. We're crossing that with the vector -1, 4, 3, which is right there. So just geometrically think about what's going on here. If we take the cross product, we're going to find a vector that is perpendicular to both of these. So to figure out the direction, let's use the right-hand rule. Take your right hand and point the 4 fingers of your right hand in the direction of that yellow vector, in the direction of A, and then curl them toward the blue vector, toward the vector B. Your thumb should be pointing directly out of the screen towards you, and that is the direction of the cross product vector. This is what it looks like. The cross product is perpendicular to both the starting vectors, and it points in the direction given by the right-hand rule. There's another geometric property happening here. If we think of the parallelogram defined by these two vectors, it would look something like that. That's the parallelogram formed by those two vectors, and the area of that parallelogram is equal to the magnitude of the cross product vector. If we find the length of this cross product vector, that is the area of the parallelogram formed by the two vectors. The magnitude of the cross product is the magnitudes of the two vectors times the sine of the angle between them, which also happens to be the area of that parallelogram. Desmos can actually compute cross products for us. Watch this. If we type in cross, and then type in the two vectors, A and B, Desmos will automatically give us that vector that we just found, -1, -7, 9. Let's think of finding the cross product in the other order. What if we find the cross product B cross A? What does that look like? Well, if we find B cross A, it looks like this. It's the same length vector, it's just in the completely opposite direction. It's also perpendicular to the two starting vectors, but to find the direction of B cross A, we'd first take our 4 fingers, point them in the direction of B, that's that blue vector, and then curl toward the yellow vector, and the direction that we get is given by that vector that we can see there. That's the vector B cross A. So A cross B and B cross A are not the same. They are negatives of each other. Their directions are given by the right-hand rule. Let's practice computing the cross product some more with example 3. For example 3, we have the vector A, which is 2, -1, 3, and the vector B is 4, 2, 1. Let's find the cross product first, A cross B, and then we'll find B cross A. At this point, I encourage you to pause the video and practice finding these cross products on your own. See if you can find A cross B and then B cross A, and then unpause the video and we'll work through them together. So first of all, A cross B. The first component is -1 times 1 minus 2 times 3. The second component is 4 times 3 minus 2 times 1. The third component, 2 times 2 minus 4 times -1. To simplify, we have -1 minus 6, that's -7. And then 12 minus 2, that's 10. And then 4 minus a -4, that would be 8. So there's the cross product A cross B. Let's contrast that to B cross A. For B cross A, we have 2 times 3 minus -1 times 1. That's the first component. 2 times 3 minus -1 times 1. For the second component, we have 2 times 1 minus 4 times 3. Then finally, in the last component, we have 4 times -1 minus 2 times 2. And now we simplify. 2 times 3 is 6 minus a -1. 6 plus 1 is 7. 2 minus 12, that's -10. And then -4 minus 4 would be -8. And compare the two answers. A cross B and B cross A are negatives of each other. They do not give us the same thing. This will always be true for any vectors A and B. A cross B will be the negative of B cross A.